Hi everybody. I'm going to make you a quick little video overviewing what's in the reading for sections 9.3 and 9.4. I think it's pretty formal in the book, but I thought maybe having a little video with an example would help bring it to life, and then it might make it easier for you to watch this and then go and that's eraser marks over there. It looks like weird little flies. It might make it easier for you to go through the work, go through the book and see what's there. Okay. So let's start with something that we already know from last year. Let's look at a pretty simple situation that we don't really need fancy physics to describe. Let's imagine we have a little box, mass M, and I have a constant force, and that part's really important, a constant F, like 30 newtons, acting on the mass. And let's say the mass is initially at some velocity, doesn't have to be zero, could be zero. Let's say I keep pushing on that block. Same force F, I don't change it. Same mass. So now obviously going to speed up, get to a V final. And I'm going to do all of that, not over a distance, the way we did with work. We looked at how forces applied over distances resulted in gains or losses of kinetic energy, or changes in potential energy. Instead, we want to look at what happens when I apply that force for a certain duration of time. So let's think about this. We know we have a law that tells us how to do this. And we could figure out things like what is, if we know V initial, what is V final, what's the change in velocity, all kinds of stuff. Let's start with Newton's second law. Because what's going to happen is we're going to be able to look at this. We're going to, even by analyzing a simple situation, we're going to see that some really interesting physics is going to pop out. And that physics is going to lead to even more interesting physics. So while it might seem like we don't need it for what we're trying to do, which is figure out the final speed of a block, we'll be able to build on this and discover some things that we didn't know before. Okay, let's write this for this particular situation. F equals ma. It's a vector equation. So now I'm going to switch over just to magnitude m times delta v. Actually, I'm not. I'm going to keep my vectors. I'm going to rewrite acceleration as delta v over delta t, just like that. And since this is nothing more than regular old Newton's second law, just rewritten out a little bit more. But now I'm going to multiply both sides by time. F times delta t equals m times delta v. And let's analyze this. First of all, let's look at this side. What is F delta T? Let's start with its units. It has units of newtons times seconds. Okay. And it actually has a name. It's called the impulse, which you might remember from last year. We talked about it a little bit. And it's often symbolized by the letter J. We did not call it that last year, J with a vector. And it's the product of the force and the time. Now what's interesting about the impulse is that you can achieve the same impulse on an object a couple of different ways. You could do it with a large force over a short time, or you can do it with a small force over a long time. So large force for a short amount of time, you got to stop. You don't have a lot of time. Big force is going to do that to you. However, if you have the time and you can invest the time, it's much more pleasant to stop with a smaller force. So whatever impulse results in, having one impulse doesn't mean it's always the same. There's a lot of different ways you can achieve the same impulse. Different forces and time combinations will multiply out to the same number. Now let's look at this side, this delta V. Let's analyze its units, which are kilograms times meters per second. So those might seem different, which might be alarming, but remember, a newton is a kilogram meter per second squared, and that times a second is going to be a kilogram meters per second. So these two are equivalent, which is good, because they should be. Let's expand this out. This is going to be mv final minus mv initial. Notice I still got my vectors because we're talking about velocities. They have sign, direction, the whole thing. Now this quantity has a name too. It's called momentum, and it's symbolized by the letter P. And this is going to be P final minus P initial. Now you might remember momentum. I'm going to define it over here. Momentum is equal to the mass of an object times its velocity. It's a vector quantity, depends on direction, and it's essentially how much stuff you have and how fast you're going. That's what momentum is. So on this side, it looks like we can shorthand that even more, and we can get a delta P. And so what we have found out is that impulse is equal to delta P. They're the same. And I'm going to write that over here. J equals delta P. And I'll remind myself that J for this constant force situation is the force times delta T. And I'll remind myself that P equals mass times velocity. So again, this is nothing but a recasting of Newton's second law. But it does allow us to talk about a problem differently. It allows us to say, okay, I can apply, if I have a certain momentum change I want to achieve, right? Because what would this be saying? Like if this had a thought bubble associated with it, let me put a little thought bubble. It would be saying something like big force with little time, or small force with big time can achieve the same delta P. Meaning I'm driving in a car, I have a speed, velocity, I want to come to rest because I have to, because I hit something or I have to stop, right? Now, if my momentum change is decided for me based on my initial final velocity and my mass, I can't change this side of the equation. But I do have some choices about how I accomplish that. So if the car hits something it has to stop quickly, my body hopefully doesn't have to stop quickly. I can hit an airbag. And what that airbag will do is it'll lengthen the impact time and also redistribute the force a little bit, but it'll lengthen that impact time and allow the force that stops me to be less than it would if I hit a more solid object and had to stop it in less time. And that's really important. That's really what's lurking partially behind this law of impulse results in change in momentum, and why it's interesting to recast it in this way. Okay, let's go on. Because you know that this isn't going to be just as simple as a constant force. Now we need to look at what's going to happen when the force is going to change. I'm going to switch to a sharper pencil. You know what they say, sharp pencil. Oop, I'm out in the window. Sharp pencil for sharp mind, which is written in Windsor somewhere near the upper school hallway. And if you don't know where it is, you have to find it. It's written on a device that sharpens pencils that you must find. Okay. So, I am going to now take a look at a different situation. Really the same situation, but just a different angle. Let's say now that I have a time-dependent force acting on my mass. And that box is still acted on by f of t at the end. It has a v initial at this point, a v final, and it's going from a time t1 to a time t2. Well, this is far more complicated now, right? Because I can't just multiply like I did up here, force and time. Because during that time interval, delta t, which is going to be t2 minus t1, I don't have the same force. So I have to do something else. So let's imagine the way we always do with calculus. Let's imagine the tiniest little time interval, you know, and instead of delta t, let's call it dt, super tiny. And let's imagine that over that time interval, the force is essentially constant. So it's a little force, it's time varying, but over that little delta t, there's essentially the world's tiniest time has a force that's essentially constant. I can still look at like my world's tiniest impulse, right? So I'm going to do that. I'm going to look at my f of t. Can you see what I'm writing still? But I'm going to multiply by dt instead. So that's my tiny little impulse, my force applied by the tiniest little time. Well, that's going to produce a teeny tiny little momentum change. And instead of writing that as delta p, I'm going to write that as dp. And just to remind us that momentum is a vector, I am going to put a vector over that. Well, this is not really helpful, right? Like we can't solve this for t because it's, you know, the tiny little time, the tiny little momentum change, but it captures an idea, right? Remember, whenever we start saying something is going to change over time, but we can still sort of multiply them in little incremental steps, you know that's going to lead to an integral. And so let's integrate both sides of this little equation. Let's integrate them from t1 to t2. And conceptually, we'll do the same thing on this side. Okay, well this we can't really do anything. We need to know the function, but this is the formal definition of the impulse when you're dealing with calculus. The integral of f of t dt from t1 to d2 takes the place of a constant force times the time. If your force is constant, you don't need to go all the way down here. You don't need this if your force is constant. You just come up here and multiply the two. But when your force is variable, you have to use an integral to accomplish the same task of basically saying, what's the force spread out over that time? How do I do force times time at every little step of the way and add them together? That's what this integral is doing. Now, the integral of any variable, just without anything in front of it, is like integrating. I'll just put like a little number 1 in there. 1 dp is just going to be p, just like 1 dx is going to be x, right? And so all this really is, on this side of the equation, is going to be the momentum evaluated at t1 minus the momentum evaluated at t2. Well, the momentum at t1 minus the momentum at t2, that's just p2 minus p1, and that's just delta p. So the nice part is this integral of dp is just delta p. In the end, it's just the momentum at the end minus the momentum at the beginning. That's the straightforward part. The part we're gonna have to evaluate is this part. So I'm gonna write this equation over here on the side again. J equals the integral from t1 to t2 of f of t vector dt equals, just like it did in the other case, delta p. So the delta p side of our equation, delta p is the same. But the way we calculate the impulse is what's different. A constant force times a time, when it's constant, it becomes an integral when it's not. Okay, this is going to lead to some really cool physics too. It tells you that the only way to change the momentum of an object is if you apply an impulse. We're going to see that when you combine this with what happens when two objects collide, we're actually going to see that momentum is conserved in all collisions. But that's ahead of the game. Let's do an example. Okay, I'm going to sharpen up my pencil before we do an example. I don't know why I'm so excited about my pencil right now, but I'm going to sharpen it up. You could show you. I don't know why I'm showing you that I'm sharpening my pencil here. Okay. Let's look at an example of an object, mass 2 kilograms, let's say. I apply a force F of t, and let's say it starts at t equals 0 with v equals 0, keep it simple, and that force is continuously applied over some time t, till we get to t2. Now let's think about what we want to analyze here. First, I'm going to give you the function of the force. Let's say the force is equal to 12 minus 3t squared. That's an interesting force. Let's first analyze it for a second. So, what's the force at time 0? Well, it's just 12 newtons, because when we plug in 0 for t, that's what we get. So it starts out pretty high, 12 newton force on a 2 kilogram object. Our initial acceleration would be 12 divided by 2, or 6 meters per second squared. But as this goes and t increases, the force is going to decrease. And in fact, there'll be some time at which the force equals 0. Let's figure out when f of t equals 0, because let's analyze the force from when it starts to when it becomes 0. Let's figure out what happens in that time interval. So to find the time when the force is 0, that's going to be 12 minus 3t squared is 0. So 12 equals 3t squared. You can see I picked these numbers. Nice, that'd be nice. Okay, so 2 seconds. Let's analyze this then from t equals 0 to t equals 2 seconds. Let's figure out the impulse first. That's the first thing we can do. All right. So if I want to figure out the impulse, the way I do that is by evaluating my integral. I can't use this equation because my force is variable. I have to come over here. I have to use my integral. J equals 12 minus 3t squared dt. That's the force dt from 0 to 2 seconds. And that's just going to be the integral of 12 dt minus 3. Let's evaluate that integral. So it's going to be 12t minus the integral of 3t squared dt. Well, 3t squared is 3t cubed over 3, so that's going to become t cubed. And that's evaluated from 0 to 2 seconds. When I plug in 2 seconds, I get 12 times 2 is 24 minus 2 cubed, which is 8. 24 minus 8 is 16 Newton seconds. And then I would minus the same function evaluated at 0. So the function evaluated at 2 minus the whole function evaluated at 0. Well, it's just 0, so my answer is just 16 Newton seconds. That's my impulse. Now I know J equals delta P, so 16 kilogram meter per second, if I want to switch to more typical momentum units instead of Newton seconds, is my delta P. And that's going to be P final minus P initial. Well, if it has V equals 0 at T equals 0, my initial momentum is 0. And so my final momentum of this object is going to be 16 kilogram meters per second. I also know that momentum, and I should put a vector. My momentum is my mass times my velocity. And I just put a final there because this is the final velocity. And so it tells me my velocity at time 2 seconds is 8 meters per second. So that's cool. Let's think about one more quick thing that we just evaluated. I have about 30 seconds left. I don't know why I didn't want to make this video long. I made it actually twice, and this one is turning out to be just as long as the other one. Let's think about what we calculate. If we graph time and f of t, if we have some function, any function, f of t. Well, remember what we're doing. We're doing the force at a certain time times like a little strip of time, and then we're adding that up over the graph. So what we're really calculating when we're calculating impulse is the area under the curve. Just like when we calculated work in a force distance graph, we were calculating the area under the curve. If your function eventually falls below the axis, let me extend this. Let's say it did that. This portion over here, when you calculate the integral, would be negative impulse. It would be a negative force undoing what the positive part did. You would just, calculate it, subtract. And so that's what you're really doing when you're calculating impulse. You're calculating the area under a force versus time graph, just like work was an area under a force versus displacement graph. So this is helpful because sometimes you don't need calculus at all. If you have a little function, for example, like in your homework, that looks like this, that goes like this, well, you can calculate the area of triangles and rectangles without the need for calculus. Similarly, if it's constant, you don't need anything fancy. It's just the area of a rectangle, right? And so impulse is also the area under a force versus time graph. I'm going to come back up here. Here's our impulse. This is also the area under an F versus T graph. Okay, that's it. I hope that was helpful. I think it'll help you with your homework. And thanks for watching, and I'll see you on Thursday. Bye.